Hey team, welcome to this tutorial on polarity. Thought I'd show face this time for no particular reason, but here I am, here you are. We're going to learn about everything to do with polarity in chemistry. So if you can look at this document that I have here, number 1, let's look at this little section of the document. Polarity, just in general, refers to anything that has basically two opposites. Okay, if you think of a bar magnet, we've got a north end and a south end. If we think about our planet, we've got the North Pole and the South Pole. They're polar opposites, and so in chemistry we can apply that same concept to bonds and molecules. One end of the molecule is completely opposite in terms of its charge or dipoles to the other end. And you can see that here, we've got two bonds over here. And in the first bond, we can see we've got a hydrogen that has a plus symbol looking thing over here, and that's known as a dipole, okay? This fancy looking musical note thing is a dipole. And so we've got a positive dipole on one end and negative dipole on the other. So that makes it a polar bond because of the two opposite dipoles this bond has. If we look down here, we've got two chlorine atoms and they both have a negative dipole. And so, because there are no opposites within that bond, this is a non-polar bond. Okay. So you might be wondering now, what the heck is a dipole? What is its reason? What is its purpose in the world of chemistry? Well, let's follow this arrow to number 3. A dipole is essentially a symbol which represents the electronegativity of something, okay? And so I'm definitely going to unpack what electronegativity means, but for now, I want you to understand that a positive dipole, like we saw in our diagram before, means that something is less electronegative, and a negative dipole, something that has a negative dipole, means that something is more electronegative. And that might seem a little bit confusing right now, but it's going to make sense. Just stay with me. Electronegativity is basically represented by a positive or a negative dipole. But what is electronegativity? That's the question that we're going to ask ourselves today. So electronegativity is basically an atom's ability to draw electrons to itself. Okay, if you want to think of it as like a personality trait that this electron or this atom has, it's its ability to attract electrons to itself. And I really just cringed at myself earlier in the year when I used an analogy which I'm debating whether I should bring up now or not, but I will. So basically, if you think of an atom, how is it able to basically have enough Rs to attract electrons to itself? Okay, what is its level of Rs in order to attract electrons to itself? Cringe, but now you're going to remember. Thank me later. Okay, so in this case, same thing applies. How is an atom, what is the level of attraction that an atom has in order to draw electrons to itself? Okay, so, and that's what electronegativity is. And as you can see, I've kind of highlighted here that electrons are negatively charged. And so in order to attract negative electrons, it's the positive protons within the atom that is actually drawing in the negatively charged electrons because opposites attract. Okay, so electronegativity, electro will stand for electrons, and negativity is the fact that electrons are negatively charged. And so electronegativity, putting it all together, is an atom's ability to attract electrons, negative electrons. So that's essentially what electronegativity means. But how is it represented by these dipoles? Let's unpack that a little bit more. I've made a little bit of a table here. I want you to focus on this section of my notes. And so basically, let's look at what happens if an atom is described as less electronegative. Okay, so if an atom is less electronegative, this means it has less of an attraction, or it's able to attract electrons very poorly. It has less attractive ability. It has less Riz or whatever, okay? So it has less attraction to negative electrons. And so because it's not able to attract electrons that well, that means that overall, the charge of this atom is going to be slightly more positive. The reason why is if you think of a friend group, okay, if you're not attracting negative toxic people into the friend group, overall your friend group is going to be a positive bunch of people hanging out together at lunchtime, okay? And so in the same way, if an atom is less electronegative, that means it's attracting less negative electrons to itself, and therefore it's going to be slightly more positive. Okay. As a result of that, this is why something that is less electronegative has a positive dipole assigned to it. If we look on the flip side, what happens if an atom is more electronegative? Well, if an atom is more electronegative, remember electro means electron, negative is obviously the negative charge on an electron. If an atom is more electronegative, this means that it's able to draw in more negative electrons to itself. Okay, it's going like this. If it's more electronegative, it is attracting more electrons to itself. And because electrons are negatively charged and you're attracting this negative particle, this means that the overall charge of this atom is going to be more negative. That's why you assign things that are more electronegative with a negative dipole, all right? And so this is why a positive dipole means that something is less electronegative, because it's not drawing in any electrons, and this is why a negative dipole means that something is more electronegative, because if something is drawing in more negative electrons, it's going to be overall more negative. So that's what we have covered so far. We understand what dipoles are. We know how to assign them. I guess the next question is, now that we've learned about electronegativity, how can you actually determine what atoms are more electronegative and what ones are less electronegative or have less Riz? I cringe at myself every time I have to say that, but here we are. Anyways, so the answer to that question is, in order to understand what's electronegative and what's not, you need to understand the trends on the periodic table. And so I've highlighted just a few to sort of uncover and unpack that question. Basically, if we look at this first bullet point, anytime you're going from basically left to right, okay, when you're going in this direction, can you see how it's getting warmer? It's got these warm colors. When you go from left to right, you are increasing in electronegativity, okay? The reason why, for those of you who want to know why, is this is because as you go from left to right, you can see that the atomic number is increasing, okay? And so it's increasing to the point that if you have more positive protons, which is reflected by that atomic number, if you have a higher atomic number, you have more protons essentially. And so because you have more protons in the nucleus, this has a stronger attractive force to any surrounding electrons around it. And so the more protons you have as you go from left to right, the greater electronegativity of that atom. And so you might be wondering, why then are most of the electronegative atoms found up in this top corner and not at this bottom, when these are the atoms that have more protons? Well, I've covered that in the last bullet point here. As you go down, the atoms are less electronegative, and the reason why is because as you go down, you not only have more protons packed into the nucleus, but you have more electrons which are found in shells, okay? And so because there's heaps, if we get to these atoms down here in the bottom right, you can see that these atomic numbers are relatively large. You've got lots of protons and electrons. And so because you've got lots of electrons, you need to fit them into more shells, essentially. Okay? And because of more shells to house all these electrons, this is actually causing a bit of shielding between the inner protons and the ability to attract surrounding electrons around it because of that shell shielding due to having lots of electrons, basically. Okay, so those added numbers of shells essentially obstruct or cause shielding between the protons in the nucleus and the surrounding electrons. And that's why as you go down, you kind of increase in electronegativity, but also decrease in comparison to the top right. I've also stated that if you go from left to right, you decrease in electronegativity because you're decreasing in the number of protons and you have less shells as well. You're decreasing in the number of protons. So those are a few trends to just keep in mind. And if we go down here, I want you to know the most electronegative atoms. You could see this up top in the red. We've got these atoms up here. And so if you're wanting to know the top 4 electronegative atoms, you should remember these ones over here. We've got fluorine, oxygen, nitrogen, and chlorine. And so these are the most electronegative, and they're ranked in this order as well, with fluorine being the most, and then second is oxygen, third is nitrogen, and chlorine is the 4th most electronegative atom. This is particularly handy, especially when you're looking at bonds and trying to decide which is the positive dipole and which is the negative dipole. Usually within a bond, because these guys are the most electronegative, they will be assigned a negative dipole, okay? And so here we are. Let's look at some non-polar and polar bonds. In this example, I've given a polar bond as an example. And so we've got magnesium and we've got chlorine. Magnesium has a positive dipole and chlorine has a negative dipole. And the reason why is because we can see that chlorine is in our list of the most electronegative atoms, whereas if we look on the periodic table, magnesium is all the way over here, okay? And we know that anything on the left-hand side of the periodic table has very low electronegativity. They are not able to draw in electrons, as well as the stuff on the atoms on the right. Okay, so I've assigned those dipoles to show that magnesium is less electronegative and chlorine is more electronegative. Okay, so here we are, we've assigned dipoles. You should ask yourself, are they the same dipoles or are they different? As you can see, they're polar opposites. Okay, so I've written a note here. If you've got the same dipoles, then that's going to be non-polar, and that's usually going to occur when you have the same atoms. Okay. So the same atoms will often give same dipoles, which means that it is going to result in a non-polar molecule. Like the example up here, I've got 2 chlorines. They're both electronegative, but because they're the same level of electronegativity, they are not polarized in any way. So that's why it's a non-polar bond. And so basically, if we look at 2 different atoms, they're most likely to have differing levels of electronegativity. And so in this case, we've got magnesium as positive dipole and then chlorine as negative dipole. And so you need to draw an arrow to show the direction of electron pull. So because chlorine is more electronegative, it is going to pull the electrons closer to itself, which is why this arrow is in this direction. It's winning the tug of war in a way. Okay, so there we are. That is essentially how you draw a polar bond. And if you want to look at an example for a non-polar bond, you can scroll up in the document that I provided. Okay, now we're up to the last little segment of this tutorial. So far, we've learned about dipoles, we've learned about electronegativity, we know how to assign them, we know the trends of the periodic table. All we need to learn right now is how can you determine polar molecules and non-polar molecules. So we know how to determine polar bonds and non-polar bonds, but what about as a whole molecule? So I've made a little bit of a checklist for you. So if you look at an atom and you notice that it has different atoms around the central atom, okay? If it has different atoms around the central atom, you can basically understand that it has all these polar bonds, and so it's likely to be a polar molecule. If it's got different atoms, it's going to most likely be a polar molecule because of the difference of electronegativities between each atom. Okay. A polar molecule will almost always have an unsymmetrical shape. Okay. And how do we know if something has an unsymmetrical shape? If you look and see, usually things that have lone pairs of electrons like this around the central atom means that the bonds aren't arranged symmetrically around that central atom. Okay? And so to find out if something is unsymmetrical, you just have to check whether it has lone pairs or not. If it has lone pairs, boom, it is unsymmetrical in shape. So if it's got lone pairs, as I've said before, it's going to be unsymmetrical. And so if it's unsymmetrical in shape, this means that the polar bonds are essentially going to add up. Okay, they're not going to cancel each other out. They're going to add up to create an overall molecular dipole. And you're gonna understand this a lot more once you tackle some past exam questions. But this is a criteria for identifying a polar molecule. Something I want you to watch out for, I've written that here, is that some polar molecules are actually symmetrical in shape. Okay, and you can find polar molecules that are symmetrical just as long as the atoms around that central atom are different. Okay, so it still has to meet that criteria of having different atoms around the central atom. Okay, you cannot find a polar molecule that is symmetrical and has the same atoms around the central atom. Okay, so that is something to really keep in mind. What are symmetrical shapes though? Okay, so I've drawn all the shapes you kind of need to know in level 2, and basically you can see that any shape that has no lone pairs is going to be symmetrical. Any shape that does have lone pairs around the central atom is going to be unsymmetrical. Okay, so speaking of this symmetry, non-polar molecules have to have the same atoms around that central atom. They also have to be symmetrical in shape, and they can be any of these as highlighted. Since there are no lone pairs of electrons around the central atom, the effect of the bond dipoles actually cancel out. And so there's no overall molecular dipole. And I want you to think of a tug of war analogy. If you have two teams on either side of a rope and they're pulling with equal strength, okay, absolutely identical, okay, no one's going to win the tug of war. They kind of cancel each other out. And because of that, there is no polarizing or opposite team. And so overall this tug of war is going to be non-polar in a way, okay? And so that's essentially how to identify between polar and non-polar molecules. So these points are super important to remember and watch out for. What I'm going to do now is I'm going to do a practice exam question. I'm going to flash it up on the screen for you, and you can use that as a template to answer these questions to excellence, and hopefully it makes more sense to you. So watch out for that. It's coming up real soon. Okay, so I just wanted to draw your attention to this because it's going through what you should or could write for your polarity questions that you might come across in your exam. And so I've got 3 different examples. This is just a mind map for study. And so basically, if we look at this first example, we've got this molecule over here. Okay, we've got this molecule over here, and basically we have to explain whether it's polar or not. So on the side, this grey part, I've kind of outlined what you need to write within your answer to cover everything. So the first thing that you should talk about is the number and type of polar bonds that are present. And so as you can see, this molecule, we have the central atom C, and around it we've got a few polar bonds. We've got two CH bonds, and then we've got two CCl bonds. And so I've highlighted that and explained it here in the first section. I've said there are two polar CCl bonds and two polar CH bonds around the central atom C. What you could do as well is include the dipoles within that bond that you've discussed. That would be pretty cool to add. Next section, you need to talk about electronegativity and explain how the polar bonds are basically electronegative in terms of what's positive, what's negative dipoles. Okay, so in each of the CCl bonds, Cl is the most electronegative, which means the electrons are more drawn to Cl than the carbon. So I've explained not only which one's more electronegative, but which one is drawing more electrons to itself. So basically I'm explaining what it means for Cl to be more electronegative, okay? This results in Cl having a negative dipole and C a positive dipole, hence a polar bond. So that's the level of detail that I want you to write to. Not only assigning dipoles, but explaining why you assign those dipoles and to what specifically. In each of the CH bonds, C is the most electronegative, which means that electrons are drawn more to C than H within that bond, just focusing on that bond. This results in C having a negative dipole and H having a positive dipole, hence resulting in a polar CH bond. So that is the polar bond that we're focusing on, as well as the CCl bond. Okay, easy peasy. Now I just have to justify the symmetry, okay? So what I've written here is I've referred to this shape. We can see, based on the fact that there are 4 bonding regions and 0 lone pairs, this is bound to be a tetrahedral shape. And if you don't remember your shapes, go back and revise that. That's super important. So I'm saying that although the shape of this molecule is tetrahedral, which is symmetrical, it is still a polar molecule because of the different atoms around the central atom, okay? So what I've written here is that although the tetrahedral shape of this molecule is symmetrical, there are different polar bonds, and I've specified that again, around the central atom. As a result of that, the effect of the polar bonds do not cancel out, which results in an overall molecular dipole. Okay, and what do I mean by the fact that these polar bonds do not cancel out? If we look here, we know that out of the CH bond, okay, out of the CH bond, let me just get another color. We know that out of the CH bond, the carbon is more positive, and then we've got the hydrogen, got that around the wrong way. We've got the carbon, which is more electronegative, so it's got the negative dipole, and then the hydrogen is positive in terms of electronegativity. And so the direction of electrons being drawn will be towards the carbon, okay? But between the CCl bonds, the direction of those would be in this outer direction here. And because all of those arrows are going in different ways, okay, they're not all going out or not all going in. Because of that, those vectors, essentially you can consider them as vectors, they actually add up, okay? They cannot cancel each other out fully. And so here we are. As a result, the effect of the polar bonds, or the bond dipoles, do not cancel out. And so that's why there is a molecular dipole present. Therefore, this molecule that we're looking at, CH2Cl2, is polar. All right, so that's an example when you can get a symmetrical shape, but it's still polar as a molecule because of the fact that they have different atoms. Let's look at the next example. We have this molecule here. It probably looks very familiar, but it's because it's H2O. And so first step, always address the polar bonds. There are 2 OH bonds around the central atom oxygen. Okay? Electronegativity. Since oxygen is more electronegative than hydrogen, electrons are more drawn to the oxygen than the hydrogen. This gives the oxygen a negative dipole and a hydrogen a positive dipole. If you're still confused about what's electronegative and what's less electronegative, always look at the periodic table, understand the trends, know that FONCl are the four most electronegative atoms. I like to spell it out as FONCL to remember them, and so that's how you know what's most electronegative and what's not. Justify the symmetry and shape. Even though H2O has the same polar bonds around oxygen, the shape is bent with two lone pairs of electrons, which results in these polar bonds not being symmetrically arranged around oxygen. Another way to write that is that even though H2O has the same polar bonds around oxygen, the bent shape is actually unsymmetrical. Okay, this bent shape here is unsymmetrical. I'm not going to fit that all in, but you get what I was trying to write there. It's unsymmetrical, okay? So because this is unsymmetrical due to the presence of these lone pairs, even though it has the same polar bonds around it, this means that this is going to be a polar molecule, okay? Since H2O is not symmetrical, the effect of the polar bonds do not cancel out, which results in the overall molecule being polar because that molecular dipole does not cancel out. That's why water is polar. Last of all, we've got this molecule over here. So we've got 4 polar CCl bonds with the central atom C. Since Cl, that's a hard thing to say, since chlorine is more electronegative than C, electrons are more drawn to the Cl than C. This gives Cl a negative dipole and C a positive dipole, hence forming a polar bond. Justify the symmetry. CCl4 has a symmetrical tetrahedral shape and the same polar bonds around C, which results in these polar bonds being arranged symmetrically around the central oxygen atom. Explain what happens to the polar bonds and how it influences the molecular dipole or not. Since this molecule is symmetrical in shape and has same polar bonds, the effect of the polar bonds cancel out, which results in no overall molecular dipole. Therefore, Cl4 is nonpolar. So if you use this criteria to explain polarity, you're going to be okay. Just follow what's in grey. You might want to come up with an acronym to know what to talk about in each box, okay? But see if you can apply these to other exam questions. Let me know how you go. I'm happy to give you feedback. Just email me and hopefully that makes sense. All right, that is all for today's tutorial.